Thank you, and I will talk about porosity in carbohydrate polymers, and in particular, I'll try to show that porosity in wet and dry states, they are completely different, and it will be based mostly on this article which we published recently, but also on some other previous works. So in our lab, we often study hydration, and well, what do we really study when we study hydration? We study quite different things for different purposes, and often we look at hydration of powders, different levels of relative humidity, and during hydration we can see often transitions which include various crystalline, gel, liquid crystalline phases, and so on. And one of practical applications often appreciated by pharmaceutical industry is encapsulation of proteins and other biologics in carbohydrate polymers. And then there is often a question, if our material has certain porosity that we let's say determined using nitrogen sorption or something like that. So how is it relevant for the encapsulation of let's say proteins? And I will try to show how wet and dry porosity in these materials are related, and how one or the other is relevant for encapsulation of proteins. So I can show you some data that we obtained quite a long time ago in 2007, where we did nitrogen sorption and also water sorption by nanomaterials with the permanent porosity, MCM41. You can see it here on that side, and also microcrystalline cellulose. You can see it on the right-hand side. And well, the sorption isotherms have different shapes if studied by water or by nitrogen, but they all exhibit quite a high amount of gases which they can absorb these materials. But in case of carbohydrate-based material like microcrystalline cellulose, we actually see that the nitrogen almost does not absorb anything in comparison to water, and water is absorbed like orders of magnitude more than nitrogen. And then we can distinguish between two different types of porosity. We can call it permanent porosity in case of silica-based materials, and here non-permanent porosity or water-induced porosity in case of carbohydrates. So essentially, in the case shown here, the porosity does not always exist in the dry state, but when we add water in certain amounts, water makes this porosity, and by that we can say that porosity here is wet. Then these two different cases we can describe by two different models. Langmuir model for the case of adsorption between solid and solid interface, and PET and related models for adsorption at solid gas interface. Again, here it's permanent porosity, and here it's induced porosity, when water can penetrate into the space between the material and the nitrogen cannot. We also proposed the model for hydration of microcrystalline cellulose, where water is adsorbed between the microfibers here, which have nano size, and by using the same Langmuir model that I mentioned, one can actually calculate the size of this microfiber. So this is in quite good agreement with the structural data on X-ray. And interestingly, the same mechanism of water absorption occurs in dehydrated proteins. For example, here we have screenshots from molecular dynamics simulation in a liquid where lysozyme molecules have native shapes. They're just oriented differently in these molecules. But when we dehydrate it, the lower picture is unfortunately schematically. The molecular dynamics was not properly done there because it requires long times, but this can be rather considered as a cartoon which shows what happens to the proteins when they are severely dehydrated, and what happens is they lose their native shapes and adjust their shapes to each other in order to fill the space. And again, if you noticed in the previous slide, the water in between the proteins was more or less arranged in monolayers, and then we can again use the Langmuir model to describe this absorption. And here we also proposed a modified criterion for applicability of Langmuir model in such systems. But then recently we started to collaborate with a company called Magle, which later changed its name to Magle Chemoswed, and they produce cross-link starch microparticles, or they also call it microspheres, and they primarily intended for drug delivery, but also for applications in surgery and so on. And when we are talking about applications for drug delivery, it's good to understand if proteins, let's say if encapsulated proteins would be able to penetrate the pore of the porous structure of these microspheres. And then the question is, if we determine porosity in the dry state, would it be relevant for encapsulation of proteins if the encapsulation itself is done actually in the liquid? So we took several batches of these materials with different sizes shown here. This is diameters of the spheres. They are actually rather big, up to half millimeter. And this is the sizes in hydrate state, but the figures on the left, they are of course in the dry state, electron microscopy figures. And also those different particles have different degrees of cross-linking, so they can adjust their properties in order to be able to use them for different applications. And well, if we start from dry porosity, one can try to visualize just using electron microscopy. And you can see on the left a figure which shows that there are some holes in the structure, and those holes are distributed well differently depending on the placing of the microparticle. And you can see here is closer to the surface of microparticle, there are no pores, but then we have larger pores, and then closer to the center we have a material where we cannot really distinguish what kind of porosity we have, because the pores, if they exist, are very small, but the surface has different texture compared to what we have at the surface. Another microscopy slide again illustrates a difference in porosities in different parts of the dry microspheres. And if we try to study it using nitrogen sorption, for example, the data for different types of these particles shown here, we studied it using nitrogen sorption. This column we show the surface area determined by BET method, and then we also determined the surface, assuming that the particles are perfectly spherical. So from geometry, we determined the expected surface area, and you see they are in relatively a good agreement, at least in order of magnitude, and in many cases actually just in very good agreement. And that would assume that the gas sorption happens only at the surface, which means the particles are non-porous. On the other hand, if you do helium pycnometry, so helium is a gas which has much smaller molecules compared to nitrogen, we actually see a different trend. So in helium, we don't determine the area, but we rather determine the volume and the density. And then we see that difference in the density is substantial compared to geometrical density shown here, which actually suggests that the particles are porous. So we explain these results by the fact that they have a quite dense crust on the surface, which does not allow large molecules of nitrogen to penetrate through the surface. And then those cavities you can show here, you can see here they are not accessible for nitrogen, but they can be accessible for helium. Okay, and then of course, if it's not accessible for nitrogen, it will not be accessible for larger molecules like proteins. But the point is that encapsulation of proteins and such materials should be, of course, done in the hydrated state. And in the hydrated state, the properties of porosities are completely different. So if in the dry state, the pores are filled with air, in wet state, the pores are filled with water. But then the question is it the same pores or they're different? And well, the answer is partly was given in the previous slides where we showed that for another material, of course, but still based on carbohydrate, the porosity is non-permanent, the porosity is induced, and then the pores are physically different. But how can we characterize the porosity in wet state? Firstly, I will show you some slides here showing the process of hydration. I actually started the video. I hope you can see it. The video is quite slow, so we can skip it and not go into the end, but it shows that when we apply water to dry particles, water starts to gradually penetrate the core, and I hope you clearly see the front which protrudes from the sides towards the center, and this is actually our process of hydration. And the hydration happens in non-Fickian way, which means in a way which does not obey the Fick's law because of the presence of glycostate. So you can clearly see move in front. This is case 2 diffusion. And we also can see a difference between those two different particles. A difference between them is that here we have kind of dark area and here we have transparent area. And this is because the particles have different history. The particle which is on top, we first hydrated before this experiment and dried, but the particle below we used as it is. And then we believe that in the particle which is here on the bottom, we actually had the porosity which contains some air, and then water comes from the sides. It actually traps the air inside the particle, and then we can see it. But in the particle here on top, this process happened in the first case when we hydrated it for the first time, and then it didn't have any air trapped in the dry porosity. In any case, the end state for both particles is the same, transparent, and then water, then the air disappears here, probably by slow diffusion through the water. And the difference in colors here, as you can see in the center, we believe also comes from the presence of porosity, because if porosity exists on the nano level, it should scatter the light, maybe make it a bit colored, because porosity in the nano level means, that the wavelengths of light, which have the same order of magnitude and size, they should be scattered in it, which produces this color. So this is one more evidence of dry porosity. But coming back to the wet porosity, so we also try to quantify it using small angle X-ray scattering, and you can see some Sachs curves here at different water contents, and I will show you in the following slides how the Sachs curves develop from fully dry to fully hydrated state and how we can relate it to porosity. So in the fully dry state, you can see those curves. They have slope of -4, which means that scattering comes from the smooth solid interface, from the solid particle surface, but also from the pores inside. And then when we move further, at 12% of water, we actually have a strong decrease of scattering intensity here. Still, we have the same slope at the end, which means at the end of this process, we have particles which have still smooth surface, but the surface is much smaller. And well, you can see that the difference in intensity is 1 order of magnitude, but while particles do not shrink by 1 order of magnitude when we add water, obviously they actually rather swell. So what happens here, I believe it's a collapse of dry porosity. Essentially, when we reach the state which is close to glass transition, the material becomes soft, and then the dry porosity collapses because the system wants to minimize its surface tension. And then in the next regime, we have, well, no changes more or less in the surface scattering, but we have increase of scattering intensities at higher Q values, and we attribute it to scattering from the polymer chains inside the particles. Then we have one more transition, which also decreases further intensity here, and we believe that this happens when the particles come closer to each other and eliminate the interface between the particle and surrounding, for example, humid air. Instead, they form interfaces between the particles, and you can see it here. It looks like more or less a forms structure, right? So we form flat interfaces between the distorted particles. And finally, when we go to fully hydrated states, the particles regain their spherical shapes, and we get this type of curve where the scattering from the surface is minor, because the surface, we can see it in the picture, but actually the physical difference between the state inside the particle and outside is minor. But the large scattering happens in the middle Q range, where we believe it comes from the internal interactions between the polymer chains. Well, can we model it and characterize quantitatively? And the answer is yes. So all these curves we show here, we actually modeled using this model, which considers scattering from the surface and from inside the particles, and from inside the particles we use so-called Gauss-Lorentz gel model, which we found in literature. We did not invent it ourselves, but it looked like it was very good for describing porosity in our system, in particular wet porosity. So this is the results of the modeling. we have two parameters, two main parameters which have physical meaning is so-called static relation length and dynamic relation length. And we interpret it as a static relation length is related to the distance between crosslinks, and the dynamic relation length is related to the distance between individual chains. So you can see that with increase of water content, both parameters grow, and they reach quite substantial values. And as you see here, the distance between the chains would reach something like 50 angstrom or 5 nanometers. And since it's a dynamic relation length, this can actually fluctuate and open for larger molecules which can be encapsulated. So in any case, this shows that porosity in the wet state is in the order of magnitude of few nanometers, while in the dry state, we saw the porosity in the order of magnitude of hundreds of nanometers. But on the other hand, the amount of porosity is much larger in the wet state, even though the size of pores is much lower. Well, the main conclusion that the wet and dry porosities in carbohydrate materials are fundamentally different, and we also propose some ways to quantify both of them. So this is the slide with acknowledgement to postdocs, PhD students, and colleagues, and funding, and thank you for your attention.